We are the University of Iowa Robotics Club. Over the last year, we brought together a diverse group of students to design and build our new rover. Fueled by our knowledge and contacts gained from participating in the Canadian International Rover Challenge during August of 2019, we've brought on promising new members to aid in overhauling the entire rover, from mechanics to control, and we believe this has positioned us to be a competitive team for this year's University Rover Challenge. Our previous chassis had an extruded aluminum frame with 2 rockers and a 4-wheel swerve drive. At the CIRC, we experienced a lack of precise maneuverability, traction, and impact resistance, so this year we developed a new 6-wheel, 3-rocker suspension drivetrain. Brush and DC motors power 6 10-inch diameter carbon fiber wheels which were formed in-house using 3D printed molds with rubber tread for traction. Motor housings are made of water-jetted 6061 aluminum plates affixed to rockers made of square carbon fiber tubing for adequate impact resistance. The frame is made of hand-welded 16th-inch square aluminum tubing to provide sufficient strength without being too heavy. Bearings on the frame allow for free rotation of the rockers. We designed a modular electronics box with stacked plates that can be removed using sliding rails to allow for easy access and more space. Housed in our systems box is our Jetson. This year we've switched over to using an NVIDIA Jetson TX2 as our central hardware component, allowing us to run all program execution and communication through one module. It uses an I2C connector to control up to 16 PWM signals, which then control our Sabertooth motor controllers. The Jetson's also useful in deploying computer vision for autonomous traversal and gait recognition when combined with our Intel RealSense camera, which is equipped with an inertial measurement unit and stereo depth perception. To communicate with our rover, we'll use an off-the-shelf 8-channel FPV transmitter-receiver pair designed for video transmission. It operates in the 900 MHz range and can switch frequencies remotely. Simple commands are sent and received using Baofeng UV5R transceivers, and real-time driving is controlled with a FreeSky Taranis digital telemetry radio system. To navigate, we'll use a GPS sensor to provide the primary path algorithm with enough data to get the depth camera into range of the goal. The camera will continuously update our path and maneuver around obstacles. When in range, the RCNN will localize the goal and steer the rover accordingly. Our autonomous scripts are written in Python, with Keras, TensorFlow, and various other robotics-specific packages. Keras is used to train the RCNN to localize and recognize objects from various images taken by our camera. For the rest of the software side, the different functions of our robot are controlled by a network of ROS nodes written mostly in Python. Data enters the network from scripts managing a GPS unit, camera, and remote control inputs from our communications system. From there, ROS publishes the remote control input to our wheel, arm, and hand nodes. Our newly designed arm will be mounted low and on the front of our chassis. 2 30-inch carbon fiber tubing lengths will provide our rover with plenty of reach, and 6 degrees of freedom gives our arm great versatility. The prisms at the middle and base joints will be made from CNC'd aluminum, and they'll use encoded DC motors with 27-to-1 worm gear drive. The wrist uses differential gearing via 3 bevel gears driven by 2 DC motors. A parallel gripper driven by a DC motor connects to water-jetted aluminum grippers. When swapped with the parallel gripper, we use a 3/4-inch stubby wood boring bit inside a tube as our drill. The sharpened tube will have a ring that forces the sample out of the tube when the drill is reversed. Following soil samples from the drill, onboard tests will be conducted to determine the presence of life. First, the soil sample will be deposited on a dish and immersed in distilled water. Then, soil particles will be filtered out of the water-soil solution and separated into test tubes, where reagent will be added. 4 biomolecules will be tested for: complex carbohydrates, simple sugars, proteins, and lipids. An onboard camera will take a picture of our test tubes for our science team to analyze. Mounted on the side of our rover will be our 3D printed kits to prevent spills and cross-contamination. In the coming months, the chassis team will replace our aluminum rockers with carbon fiber tubing, add rubber tread to our wheels, and complete the electronics enclosure. The arm team will assemble the wrist, hand, and CNC prisms with the carbon fiber tubing. Systems team will implement our long-range wireless communications into ROS, apply autonomous terrain traversal with drive control, and create a GUI to simplify rover operation. Lastly, the science team will test our 4 biomarker assays and will combine the test kits with the rover for field testing. We'll be testing and integrating all of our rover subsystems in competition-like scenarios, such as by creating an arm manipulation board and a terrain traversal challenge course.
We are the University of Iowa
Robotics Club.
Thanks
for
watching.
Go Bots!